Welcome back to another session with working through practice problems from an old exam. We're looking now at problem 2 from exam number 1 from the summer of 2007. This is asking now for a Thevenin equivalent circuit, or we now need to find a Thevenin voltage and a Thevenin resistance that will look the same as the given circuit between nodes A and B. We're trying to then find this equivalent system, or essentially remodel this device from the perspective that we're not wanting to know necessarily what all's in that red box that I've just created, but we want to know what's happening as we look into the terminals A, B, and we want that behavior in terms of what's happening to be modeled by a Thevenin voltage in series with a Thevenin resistance R sub T. We can find, or start to find, that because we now know a little bit about this circuit's characteristics, this equivalent circuit. We know that V Thevenin is actually V open circuit if we calculate or can compute the open circuit voltage between nodes A and B. If we look at that, and there's many different ways that we could analyze this circuit, but just looking at this, if you're thinking, oh, I need to find this open circuit voltage right there, then you're going, well, here's a node, and here's another node, and wow, I don't want to do two nodes, but actually, if we just concentrate on that node and realize that if we just consider these two resistors in series, let's not worry right now about calculating this open circuit voltage. Let's just try to find V. If we can find V, then we'll be able to find the current flowing in that particular path, and then we can actually find via Ohm's law this open circuit voltage VOC. Or once we're given this V, we could use a voltage divider to find V open circuit. The key then for the way that we're looking at the problem now is to find that voltage, capital V, and then we'll try to obtain from that either the current in red that I've indicated flowing through those series resistors 6 and 24, or do a voltage divider and find V open circuit as a voltage divided across 6 and 24, and how much is actually split or divided across that 24 ohm resistance. Let's then try to find V in this circuit. If we want to find V, what we're now doing is nodal analysis. And for nodal analysis, what we want to do is write a KCL equation, or we write as many KCL equations as we have unknown node voltages. In this case, we've just identified the one unknown node voltage. Now you're going, well, I need to find this particular current going this way. But, and if that's the case, you would be wanting to maybe find this voltage. That voltage we don't know, but remember, we know this particular current, which is just the negative of the current that we might want to think of going out of node that we've labeled with the V node voltage going to the left out of that node. If we now look at this current coming in, that's 4 amps, that's going to equal that current going down, this current going at an angle, and this current going to the right. Let's write KCL in terms of those four currents. We have the current coming in, that's 4, equaling the current going out, which is V over 10, plus V over 15, plus, and now I can't forget that it's not just V over 6. That V is dropped across the 6 and the 24, and I need to add those resistors in series to obtain the total resistance from V, that node V, to ground, or to our reference node, which is right here. That's now my equation. I have one equation in the one unknown V. Let me see if I can rewrite that. I have 1/10 plus 1 over 15 plus 1 over 30 times V. If I now multiply everything, 30 looks like a nice multiple to multiply everything by, so I now have 4 times 30. That's going to equal 3 plus 2 plus 1 times V. And now I have 6 there, and I have 120 there, or V now becomes 120 over 6, or 20 volts. If V is now 20 volts, that's dropped across these two resistors, 6 and 24. Or I could say, let me call this I sub, I don't really know what I want to call it. Let me call it I sub 1. And now I could say, oh, I sub 1 is now V divided by 6 plus 24 for the sum of those two resistors. This is 20 divided by 30, or I sub 1 is now 2/3 of an amp. If that's the case, then V open circuit is actually going to be the 24 volts that we want, that resistance, or the voltage drop across. It has a resistance of 24 times I sub 1. We have 24 times 2/3, or 16 volts for our open circuit voltage. We could have done a voltage divider. We don't have to do it. We could, to check our work if you have extra time. If you do a voltage divider approach to finding your V open circuit, that's going to be the resistance that you're interested in, which is 24, and the sum of all the resistances in series, all times the total voltage dropped across all of the series resistors, which in this case is 20 volts. We now have 24 over 30 times 20, and this is saying, well, let's just say that's 10 and this is 8, and there's 2, so that we now have 16 volts for our open circuit voltage. We now know half of the answer. We now know that in our equivalent, we know our Thevenin source voltage, that's 16 volts. What we don't know is this Thevenin resistance. But we can start to get a feel for that if we go back to our circuit. Let me just go ahead and sketch it. And now that you've already solved some or written some KCL equations, it might be just as quick to go ahead, now that you feel pretty comfortable writing those equations, it may be just as quick to try to find this short circuit current between nodes A and B. So we short this out, and we want then the current I short circuit flowing through that particular path in order to obtain the second variable of interest is I short circuit. We can then divide that into V Thevenin to obtain our Thevenin resistance. This resistor was 10, this was 15, this is 6, This is 24. The issue that you need to worry about here, if this is now our V, now we're analyzing a different circuit now because we've changed it. We've now put a wire between these two nodes, A and B. We've shorted those out, and now any current that's coming here is wanting to be divided between 24 and a short, but that short is presenting zero impedance to that current flowing, and so all of this current is actually going to go to that I short circuit current, and this 24 is effectively removed from our system. It looks to be infinite in impedance, which means that we need to change our equations just slightly when we write our KCL equation. Now writing KCL for this node voltage V, we have 4 coming in, that's this current. The current coming out going down vertically is V over 10. The current going at an angle is now V over 15. And now what we have to realize is that this voltage V is no longer divided or split between 6 and 24. Now it's split between 6 and 0 in terms of the resistance that it sees. So we now have V over 6 for our last current, which is the current going horizontally to the right. We can now collect some of these terms, and I liked multiplying by 30. Let's just go ahead and multiply by 30 again. So I now have 3 plus 2 plus 5 times V, or this quantity now becomes 10. This is 120, so that V, with that one resistor shorted out because of the I short circuit condition, is now 12 volts. That's now, let me call it V sub 1 so you don't confuse it with the unit's voltage. Now that we have V sub 1, we can use that to find this current flowing, which is the same as our short circuit current. Our I short circuit then is going to be V1 over 6, or we now have 2 amps for our short circuit current. Because of the relationship that we know, if we go back to our Thevenin equivalent, here's our Thevenin source voltage, here's R sub T, and here are terminals A and B. What we've now learned is if we short this out, this short circuit current is going to be 2 amps, and this voltage we just computed earlier was 16 volts. Now we can use that information because this voltage is dropped completely across that Thevenin resistance with the short in place, and now we know by Ohm's law that V sub T is actually R sub T I short circuit, or R sub T is now V sub T over I sub short circuit, and R sub T now becomes 16 over 2, or 8 ohms. Now we're done. We can now say that our Thevenin equivalent is a Thevenin source voltage of 16 volts and a Thevenin resistance R sub T of 8 ohms. And that's now the answer that we were looking for in terms of finding the Thevenin resistance or the Thevenin equivalent circuit for that original circuit. As an additional piece to that problem, if you didn't want to solve for the short circuit current and you've now found, let's say, the Thevenin voltage, you could actually find the R equivalent by zeroing the independent sources that are present in the system. In this case, here was our circuit, there was our current source, we had a 10 ohm resistor, another 10 ohm resistor. We had another resistor that was at a diagonal. We had a horizontal resistor and a vertical resistor of 24. If we want to zero our independent sources and try to find the resistance looking into those terminals A and B, that equivalent resistance would be our Thevenin equivalent. If we want to zero out a current source, then we look at its terminals, and the way that we zero it out, a current source, is to actually remove it or open up those nodes that are associated with the two ends of that current source. That's how we zero out an independent current source. Now that we've done that, in looking back into this circuit to the left, into nodes A and B, we want to find what's this resistance that we see between. If we measured that with an ohm meter, what measurement would we see on our meter? Looking at that, this is now empty space. Or you can think of this now being in series with this resistor. Well, if you don't have anything here, then this is now an infinite impedance. And so the sum of 10 and infinity is infinite, meaning this particular piece of that particular network we don't even have to worry about. This is now gone. We don't have to worry about it, and maybe it's easier to just re-sketch the system without that particular resistor hanging off on the left-hand side. Here's our 6 ohm, here's 10, 15, and 24. This is now what we have once we've zeroed the independent source. If you look at that, we'll see that this node and this node, which is really this, are shared, or those two resistors are actually in parallel, the 10 ohm and the 15 ohm. So if we do an R equivalent between those two, we're taking 10 in parallel with 15, which is now going to be 10 times 15 over 10 plus 15, or 150 over 25. And how many quarters are in $1.50? That's one way that I like to think of that. And so now we have 6 quarters in $1.50, or there's 6 25s in 150. We now know that that parallel combination of 10 and 15 is 6. I like to just keep redrawing this. Now we have a 6 that's going to go between those two nodes that we had identified before. We then have accounted for the first vertical resistor and the diagonal resistor. This one was 6, this was 24. And now we have this easy task of combining those two resistors that are now in series. Those two, let's say R equivalent of 6 is now 6 plus 6, or 12 ohms. Let's redraw it. Now we have that series combination of two 6s reduced to one resistor of magnitude 12. We now have two final resistors that are in parallel. We can find our final R equivalent, which is actually the same as our Thevenin resistance, and that's this 12 in parallel with 24. Or now we have 12 times 24 over 12 plus 24. And now we're going to have to figure out what that is, but in That's now 36. Here's 12 and 24. Let's start getting some common factors out of there. 3 is the one that first comes to mind because of the 24, so there's 8 and 12. The 12s now cancel, and our R equivalent, which is our Thevenin resistance, is now 8 ohms, and that's consistent with what we found before. And that should